Hello viewers, Wagaruna taking you through the story of A-Level Physics Paper 2. And this video I'm going to go through the topic of Doppler effect and beats. So this video is under the topic of waves and is suitable for students in both Senior 5 and Senior 6 offering physics as part of their combination. So before we proceed, let's first look at the course outline of this paper. So physics paper 2 is divided into 4 parts. The first part is geometrical optics, where 2 questions come from these topics. Second part is physical optics, where 2 questions come from these topics. The third part is electrostatics and electricity, where 3 questions come from these topics. And the fourth part is magnetism and alternating current, where 3 questions come from these topics. So the first part, optics, was already done, electrostatics and electricity is already available on this platform, and now we are on physical optics. So wave motion and sound transmission, the calculations can be divided into 4 parts. The first part is progressive and stationary waves, which is already covered. Second part is waves in pipes and strings, which is already covered. And now we are going to cover 2 parts, which is Doppler effect and its applications, and also beats. So here we're interested in calculations, but complete notes are available in this book called Mastering A-Level Physics Paper 2. It has clear notes, worked examples, and trial questions of all the parts of Physics Paper 2. So if you're buying it, I encourage you to buy edition 2023, which is updated. So for orders of any of these copies, contact the author on any of these 2 contacts. And a complete set of physics has 3 books. There is Physics Paper 1, Physics Paper 2, and a topical question bank. Then for Principal Math, there are also 3 books, Math Paper 1, Math Paper 2, and a topical question bank. And subsidiary math, it is only 1 book, and the rest are for O-Level. So for any of these copies, contact the author on these contacts. So now shall start our topic of Doppler effect. So this video is also divided into 2 parts. There's a part of Doppler effect and a part of beats. So let's first cover the part of Doppler effect. So Doppler effect is the apparent change in the frequency of a sound note heard by the observer or listener when there is relative motion between the source and the observer. So in Physics Paper 1, under mechanics, we must have covered the topic of relative motion or relative velocity, and I believe you are now aware of that part. So here we are going to deal with what we call apparent change in frequency. So everything we want is to calculate the apparent frequency of sound note heard by the observer when there is relative motion between the source and the observer. So the observer can be in motion and the source in motion, or the observer can be stationary and the source in motion, or the observer can be in motion while the source is stationary. So there are various cases, and we shall look at all those cases. So let's first illustrate what we need. So we shall have a source of frequency U.S., of moving at the speed of U.S. and emitting sound of frequency F. And this is the observer or the listener. So the sound will reach the observer with a velocity v. So this v is the velocity of sound in air. This is the velocity of the source, this is the velocity of the observer. And this is the true frequency of the sound note from the source. So if f prime is the apparent frequency or the frequency of sound heard by the observer. Actually, this is what we shall be calculating. F prime and V prime is the apparent velocity of the sound received by the observer. So I encourage you to master these symbols because we shall use them frequently. F prime means apparent frequency, V prime means apparent velocity of sound received by the observer, and lambda prime denotes apparent wavelength of the waves or sound waves reaching the observer. Therefore, to imply that from F prime will be equal to V prime over lambda prime. So for you to get F prime, you have to know V prime and also lambda prime. So for you to get a V prime and lambda prime, you need to know the effects of the observer's velocity. So the velocity U naught, remember it was the velocity of the observer. The velocity U naught of the observer affects the apparent velocity V prime of the sound waves received by the observer. So there are various cases. There are actually three cases. One, the observer can be stationary. If the observer is stationary, it implies that the velocity of sound waves reaching the observer is the same as the velocity of sound in air. So V means velocity of sound in air. V prime means the velocity of the sound waves reaching the observer. That is if the observer is at rest or stationary. But if he is moving, the direction matters. So if the observer is moving towards the source, it implies that the velocity of sound waves reaching him is V plus U naught. So it has to increase. So for him is moving towards the source, and the sound from the source is coming this side. So the velocity reaching the observer will increase. On the other hand, if the observer is moving away from the source, it implies the velocity will reduce. So those are the three cases. One, if the observer is stationary, the velocity will be equal to the velocity of sound in air. Then if the observer is moving towards the source, then the velocity will increase by the velocity of the observer. If the observer is moving away from the source, then the velocity will decrease. Okay, that is how we can get V prime. What about lambda prime? Lambda prime is affected by this velocity of the source. So the velocity of the source, U.S., affects the velocity Vs of sound waves from the source, which in turn affects the apparent wavelength lambda prime of the sound waves reaching the observer. So there are also three cases. One is if the source is at rest, it implies that this Vs will be equal to V, and therefore lambda prime will be V over F. Remember, lambda prime is the same as will be equal to Vs over F. So F is the true frequency of this note sounded, as we saw in the diagram. Then what about when the source is moving towards the observer? So when the source is moving towards the observer, Vs will reduce. So it will be V minus Us, and implying that lambda prime is equal to V minus Us over F. So lambda prime is got by Vs over F. So Vs is this, we have to put here, over F. So I think you see that it is the opposite of the first effect. So for the observer's velocity, when the observer is moving towards the source, the velocity the V prime increases. But in this case, when the source is moving towards the observer, then Vs reduces. On the other hand, if the source is moving away from the observer, then Vs will increase. So it is just the opposite from the observer's velocity. So Vs will increase, implying that U prime also increases. Lambda prime also increases. So when we understand this logic, then we can do the calculations of questions and the Doppler effect. So shall look at cases. One is the case where both the source and the observer are moving towards each other. So consider a source of sound moving with velocity us towards the observer, who is also moving with a velocity u0 in the opposite direction towards the source, as shown below. So you have the source, we also have the observer, they are moving towards each other. So source has a velocity us and emits sound of frequency f. Observer has a velocity u0. So that will be the waves from the source reaching the observer, and they were moving at a velocity v. So v is the velocity of sound waves in air, and f is the true velocity of the note sounded. That means that the velocity of sound waves from the source, Vs, will reduce. Like I told you, for velocity of when the source is towards the observer, Vs reduces. Then the apparent wavelength of the waves reaching the observer will be Vs over f, where Vs is this, so you can substitute. So you've got lambda prime. What about V prime? So V prime, the observer is moving towards the source. What do you think will happen? So when the observer is moving towards the source, then V prime will increase. That's why there is V plus u0. Therefore, f prime will be equal to V prime over lambda prime, which will give you, and lambda prime is Vs over f, so it becomes f over Vs. So I come and substitute for V prime, Vs, and f. And this will be the expression when the observer and the source are moving towards each other. But there are cases when they are stationary. So first of all, we shall say that generally f prime is given by v plus or minus u0 over v plus or minus us times f. But since the sound, so this is the general expression of f prime. Now it is you to find out whether you put a plus here or a minus, or you put a plus here or a minus. Now how do you find out? You'll come over here and say that since the source of sound approaches the observer, the apparent frequency increases. The apparent frequency is this. It increases, and for it to increase, it means that the numerator must be maximum and the denominator must be minimum. Okay, that is one. Then to remember that for the numerator to be maximum, it has to be a plus here. And for denominator to be minimum, it has to be a minus here, which gives you this expression. So this note 1 is just to give you a brief way you can easily remember the formula which you can use, such that you don't go through the steps we have gone through. You just code the formula, substitute, and get the answer. Because whether you derive or you just code the formula, the marks will be the same. So it is better to learn a shortcut. Okay, so what I realized that this is the expression of f prime. So you ask, what if the observer was stationary? It means that it is the source moving towards a stationary observer. That means that where there is u0, we shall put 0, and we shall remain with v over v minus us, everything multiplied by f. That is if the observer is stationary. But what if the source is stationary? It implies that us is 0, as we shall see in the next slide. So if the source is stationary, it implies the observer is moving towards a stationary source. Therefore, us will be 0, implying that the apparent frequency will be v plus u0 over f, everything multiplied by f. over v, everything multiplied by f. So that is the case when both are moving towards each other. What if both are moving away from each other? So still the same, consider a source moving at the velocity u(s) away from the observer, who is also moving with the velocity u0 in the opposite direction away from the source as shown below. So we have the observer and the source, then each are moving away from each other. So that means that the sound will move in this direction so that it reaches the observer. So to be represented by that. Okay, so the expression for frequency, apparent frequency, can be derived as follows. So in this case, the source is moving away from the observer, meaning that Vs will increase. Okay, but the observer is also moving away from the source, implying that V prime will reduce. So let's see that in this slide. So let V be that, US be that, and F be that. So the velocity of sound waves from the source, Vs will increase. It will be V prime plus US, implying the apparent frequency wavelength will now become V plus US over F. However, the apparent velocity of sound received by the observer, that is V prime, will reduce. So in the end, we shall come up with F prime being equal to V prime over lambda prime. V prime is here, lambda prime is here, and come up with this. Now, still, if you look at the note, with the note 1 we made, here, if this observer is moving away from the source, and the source is moving away from the observer, it implies that the apparent frequency must keep on reducing. And for it to reduce, it means that numerator has to be minimum and denominator has to be maximum. So minimum numerator, that's why there is a minus. Maximum denominator, that's why there is a plus here. So even if you don't go through these steps, you can just code this formula, substitute, and get the answer, as we shall see in the questions. So note the following. So this is what I've been explaining. That generally F is that, F prime is that, but since the source of sound recedes means moving away, recedes away from the observer, apparent frequency decreases, implying that the numerator should be minimum and denominator should be maximum. So case 2 is what if the observer is stationary. It implies that u0 is 0, and therefore F prime will become that. Then also, if the source is stationary, it implies that US is 0, and therefore apparent frequency will be that. So once you understand this, then you can go to the calculations. So question 1 came from UNEB 2013 paper 2 question 3D Roman 2 and says, a motorcyclist and a police car are approaching each other. The motorcyclist is moving at 10 meters per second and the police car at 20 meters per second. The police siren is sounded at 480 Hz. Calculate the frequency of the note heard by the cyclist after the police car passes by. So the police car is passing by means it is moving away from the cyclist. So first of all, initially they were moving, this source was moving, okay. Initially the observer was moving towards the source. But when this source passes, it implies that now they are moving away from each other. Therefore, the source is moving, the observer is moving in this direction, and the source is moving in the other direction. That's what they mean by passes by. So when it moves away, sound still will go in the other direction so that it reaches the observer. So V is 340, which is here, U0 is 10, US is 20, and F is 480. Therefore, we shall come and quote the formula, because moving away means apparent frequency reduces, and for it to reduce, it has to be a minimum numerator, that's why there is a minus, and the maximum denominator, that's why there is a plus. Then you can substitute and use the calculator to get the frequency they wanted. Question 2 came from U.A.C.E 1996 part 2, question 3C, and it says a police car moving at a speed of 20 meters per second. So you're using the word edited because in that year this velocity was not given. Sounds a siren of 1000 Hz as it approaches a stationary observer. What is the apparent frequency of the siren as heard by the observer if the speed of sound in air is 340? So you'll come and make our illustrations. Source observer. Observer is moving towards a stationary observer. Source is moving towards a stationary observer with a velocity of 20 and frequency of sound emitted is 1000 Hz. So sound waves will move in that direction to reach the observer. Now that means that apparent frequency will increase because the source is coming towards the observer. For it to increase, it implies that numerator will be maximum and denominator will be minimum. So minimum, that's why there is a plus. And here it would have been plus US, but because plus U0, but because U0 is 0, that is why we just put V. Therefore, you come and substitute and get the output. Question 3 came from U.A.C.E 2020 paper 2, question 3D, and it says a car P moving at a speed of 108 kilometers per hour towards a stationary observer and another observer in car 2 moving in opposite direction with that same speed as P sounds a horn of frequency 256. Find the frequency of sound heard by the stationary observer and Roman 2 observer in car 2. So speed of sound in air is 340. So here still you shall make a sketch. So first of all, we shall convert the kilometers per hour to meters per second. Then shall come and make our sketch. Now these sketches I'm making, it is not a must to make them as long as you are aware of the formula which you are supposed to use. Because so it is okay to use them or it's okay not to use them. So I'll draw the sound waves towards in direction towards the observer. So that means that the apparent frequency will increase, meaning numerator is maximum, denominator is minimum, and that is why there is a minus in the denominator. So now I believe you know how to draw the sketches. So in the next videos, in the next questions, I may not draw the diagram. I'll just code the formula, substitute, and get the output. But in this I'll draw, so in Roman 2 I'll still draw. The source is still moving towards the observer, and in this case the observer is now moving with a speed which is the same as that of the source, so 30, 30. And that's what they told us in the question. So sound will move in the direction to reach the observer. So the apparent frequency increases, so maximum numerator, that's why there is a plus, minimum denominator, that's why there is a minus, to give you this as the frequency. Then question 4 came from U.A.C.E 2001 paper 2 question 3D, and it says a car sounds a horn as it travels at a steady speed of 15 meters per second along a straight road between two stationary observers, A and B. Okay. The observer A hears a frequency of 538 Hz, while B hears a lower frequency. Okay. Calculate the frequency heard by B, assuming the speed of sound in air is this. So one hears a lower frequency, meaning the source is moving away from that observer. They said B hears a lower frequency, meaning the source is moving away from B and towards A. So this is what we have. We have U.S. 15, we have Fa prime, and we have V, speed of sound in air. So when the source is moving towards the stationary observer, it implies that V prime is equal to maximum numerator, minimum denominator. That's why there is a minus. So I'll come and substitute for Fa, for V, and for US. So when I do that, I'll be able to make F the subject, and that will be the value of F. So now that I know the value of F, I'll come and deal with observer B. So when the source is moving away from a stationary observer B, then F prime will be given by this formula, substitute, and get the output. That was question 4. Question 5 came from U.A.C.E 1999 paper 2 question 3D, and it says a car traveling at 72 kilometers per hour has a siren which produces a sound of frequency 500 Hz. Calculate the difference between the frequency of sound heard by an observer by the roadside as the car approached and recedes from the observer. So approaching means towards and receding means away. So we know that velocity of sound in air is 320. This one is U kilometers per hour, so it changed to meters per second. Frequency is 500. So there are two cases. When the car approaches a stationary observer, apparent frequency increases. So possible maximum numerator, minimum denominator. So come up with that. When the car recedes from the stationary observer, then apparent frequency reduces. Minimum numerator, maximum denominator, to come up with that. Therefore, the difference in the frequencies will be got by subtraction, which will be this. And that's what they wanted. So now we shall go to estimation of the speed and direction of a star. That is an application of Doppler effect. So we shall need to derive a formula which will be used. One, we shall consider a star, so this is not start. This T, remove it. We shall consider a star moving away from a stationary observer on Earth, as shown below. So you have an Earth, which is the observer, and a star, which is the source. So the Earth is stationary, but the star is moving away. So the star can move away or towards, but for the case of derivation, we are going to consider both. We are going to consider when the star is moving towards and when the star is moving away. But let's start with when the star is moving away from the Earth. So that will be the diagram. So if the star is moving away from the Earth, the velocity cs of light waves from the star will be given by that formula. So moving away means that the source Vs, which is now Cs, will increase. Therefore, lambda prime will increase. So what is lambda prime? Lambda prime is the apparent wavelength of light waves reaching the observer on Earth in line with the star's motion. And U.S. is the speed of the star, and C is the speed of light in vacuum. Then F is the frequency of light emitted by the star. So if lambda is the wavelength of light emitted by the star, it implies that a Doppler shift, or which is change in wavelength or shift in wavelength, given by this expression can be given in this form: lambda prime minus lambda. So we already saw lambda prime, that is equal to that. So when I subtract from this to this, I'm going to split the numerator, because the whole of this is the same as C over F plus S over F, which is here. Then now remember that C is equal to Fy. Therefore, come and substitute for C here. Then this F cancels, remain with lambda, which is here. Then lambda and this one cancels, remain with US over F. So this means that change in Doppler shift is equal to US over F, meaning that I can make US the subject by taking this F this side to become US will be equal to F times Doppler shift. But F from here, we know that F is C over lambda, so we can substitute for it there. Then we shall rearrange correct like terms. This and this gives you this, and C will be outside. Then this Doppler shift, remember we said it is the same as this, so I can come and replace it there. So that is for the case when the star is moving away from the Earth. What about when the star is moving towards the Earth? So there's something will differ. One, initially it was C plus US, now it will be C plus C minus US. Therefore, the Doppler shift will be given by that, still the same formula. The substitution, it is only this one which is changing. So split the numerator to come up with that. But we know that C is equal to F lambda. Therefore, come and substitute for C here. And here it gives you this cancels, you remain with negative. Now we are dealing with a negative. So away from the Earth it is positive, towards the Earth it is negative. So we can make our conclusion that since US is plus or minus of this, the magnitude sign is introduced to eliminate the negative during calculations. That means that in general, US will be equal to the magnitude of Doppler shift over wavelength, which is given by this magnitude, meaning that when you subtract, you have to get a positive by all means. So magnitude means what is negative becomes positive. So this is the note. So when the star is moving away from the Earth, it implies that this is bigger, and therefore there is a red shift. But when the star is moving towards the Earth, it implies that this is smaller than this, and therefore there is a blue shift. So that shall go through these questions. Question 1 says a star is moving away from the Earth at a speed of this relative to the Earth. Okay, calculate the wavelength shift, that is Doppler shift, the wavelength shift observed on Earth for light of wavelength this emitted by this star. So we know that US is this and lambda is that. Therefore, from this formula, make this the subject, because that is the Doppler shift. You'll come up with US times lambda over C, which is here. Then substitute for US, for lambda, and for C. C the speed of light in vacuum. So you'll come up with this as the Doppler shift. Question 2 says a certain spectral line of hydrogen has frequency this, as measured in a laboratory on Earth. The same line in light reaching the Earth from a star has frequency this. Calculate the speed of the star relative to the Earth. So F is here, F prime is here, therefore lambda will be given by C over F, which is this, and lambda prime C over F prime, which is this. Then you can code the formula for speed, C magnitude of Doppler shift over wavelength, which gives you that. Then you can use the calculator to get the answer they wanted. So this one, it should have been a negative, but because of the magnitude we want positive. Question 3 says wavelength of light from a star observed on Earth is 600 nanometer, and wavelength obtained by analysis from a laboratory is 780 nanometer. Roman 1. Which way is the star moving, away or towards the Earth? Roman 2. Find the speed of the star. So first of all, you know that lambda prime is 600 and lambda is 780. Therefore, here lambda prime is smaller than lambda, meaning that the star is moving towards the Earth. And that will be the reason. So Roman 2, they want the speed of the star. You code the formula, substitute, and get the output, and that's what they wanted. So now shall go to what we call bits. So when two notes of nearly equal frequencies are sounded together, at some instant the waves from both nodes arrive at some place in phase and reinforce and produce a loud sound, while at another instant a compression from one arrives together with a rarefaction from the other, and a low sound or no sound is at all heard. So that means that there will be a periodic rise and fall in the loudness of the sound, and that periodic rise and fall in the loudness of the sound is what we call bits. So if you consider two notes A and B having frequencies F1 for A and F2 is for B, so that these two frequencies are nearly equal, it implies that the bit frequency F will be given by the magnitude of the difference. Magnitude means we don't need the negative. So that's be the expression for bit frequency. And with that, shall go through these questions. Question 1 came from U.A.C.E 2018, paper 2, question 3D, and says two whistles are sounded simultaneously. The wavelengths of sounds emitted are this and that respectively. Find the bit frequency if the speed of sound in air is that. So we know that bit frequency is the difference in frequencies. So it will be F1 minus F2. F1 is V over lambda 1. F2 is V over lambda 2. So substitute for V and lambda 1, V and lambda 2 to come up with this as the bit frequency. So now shall go to question 2, which came from U.A.C.E 2016, paper 2, question 3E, and it says two observers A and B are provided with sources of sound of frequency 750 Hz. If A remains stationary while B moves away with a velocity of this. Find the number of beats heard per second by A. That is the beat frequency. So what you should realize that observer A, he has two notes. One is of frequency 750 due to its own source, and he also has another one of frequency FB prime due to source B. So the one of due to his own source, it is still 750, but the one due to source at B, we shall get using this formula, because one, it is reducing, because this observer B is moving away from A. It implies that FB prime reduces. That is why there is maximum numerator and there's minimum numerator and maximum denominator to give you that. So bit frequency will be got by subtraction, and that's what they wanted. Then question 3 came from U.A.C.E 2007, paper 2, question 3D, and it says, calculate the frequency of bits heard by a stationary observer when a source of sound of frequency 80 Hz is receding with a speed of this towards a vertical wall. So apparent frequency of directed stroke incident sound will be given by that. Then the apparent frequency of the reflected sound will be given by that. So here reflected, the incident sound is moving away, meaning that it will be this will be minimum, so minimum numerator, maximum denominator. The reflected sound is towards, meaning this will be increasing, so maximum numerator, minimum denominator, and then the difference between the two will be the bit frequency, and that's the answer they wanted. So bits can also be used to determine unknown frequency of a note. So in this case, a test note F2 is sounded together with a standard note, say a tuning fork. So this is what you want to obtain. So you sound it together with a standard note whose frequency is known. So the number of loud sounds occurring per second, that is FB, are counted and recorded together with the frequency F1 of the tuning fork. Remember, this is the standard frequency, so its frequency is known, and this one is got by counting the number of loud sounds per second. So now the bit frequency will be given by subtracting the two, but you don't know which one is bigger. It can be F1 minus F2 or F2 minus F1. So to tell which is correct formula to use, one prong of tuning fork is loaded with plasticine and the procedure repeated and the bits per second counted. So then the new value will be, the new bit frequency will be FB prime. So now you're going to compare the two. So if FB prime is greater than FB, it implies that FB will be given by this formula, from which you can get F2 from this by making the subject. However, if FB prime is smaller than FB, it implies that it was supposed to be this, and therefore F2 can be got from that. So that shall go through these questions. Question 1 came from U.A.C.E 2001, paper 2, question 3C, and says, two tuning forks X and Y are sounded together to produce bits of frequency 8 Hz. Fork X has a known frequency of 512 Hz. Okay. When Y is loaded with small plasticine, bits of frequency this are heard when the two tuning forks are sounded together. Calculate the frequency of Y when unloaded. So when unloaded, the bit frequency, remember we don't know, it can be Fx minus Fy or Fy minus Fx. Now because we don't know, we shall put a magnitude there. So this magnitude will be equal to 8. When you remove the magnitude, it becomes plus or minus 8. So that means that when I take this one this side, substitute and take it this side to come up with that. So I'm going to get two values of which one is correct, one is not correct. But how do you test? You test using this part of loading. So this was when unloaded. You get two values. Then when loaded, B frequency became 2. Therefore, remove the magnitude side to come up with plus or minus. Substitute for fx, take this one this side to come up with this. So this is supposed to be plus or minus, not minus plus, just plus minus. So there are two values. This plus this gives you 114, 514. This minus this gives you 510. So this one corresponds to with this, and this one corresponds with this. So from there we shall remember that when a tuning fork is loaded, frequency must reduce. So of this pair, this and this, frequency reduced. Of this and this, frequency increased, meaning that this one is not required and this is the required frequency. So you come and conclude that Fy cannot be 504, therefore it is 520. Okay, then question 2 came from you. It says when a tuning fork of frequency this and a guitar string are sounded together, beats can be heard with a frequency of 3 Hz. When the guitar string is tightened slightly, the beats increased to 4 Hz. What was the original frequency of the string? So still initially, before tightening, we have Fs minus Ft, frequency of the string, frequency of the tuning fork. So remove the magnitude side to become plus or minus, then substitute for Ft to give you that. Make Fs the subject, you will get two values of Fs. Okay, then when tightened, still we shall put magnitude, remove the magnitude, substitute for Ft, and make F prime S the subject. So there are two values still of Fs. So this one corresponds with this, and this one corresponds with this. Now because the string was tightened, frequency must increase. So if you look at this, from here to here it increased, from here to here it reduced, meaning this is not required and this is required. So you come and conclude that Fs cannot be this, therefore it is that, and that's what they wanted. So that brings us to the end of this video. Thank you for watching, and bear in mind the next video will be on wavefronts and their properties. So if you have not yet subscribed, please click on the subscribe button below this video so that I can receive updates when the next video has been uploaded. And also, if you know of any student who's not yet on this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp, so that we can all benefit as a family.